Hi everyone, welcome back to the Coding and Analysis YouTube channel. And in today's video, we're going to run our XGBoost model with cross-validation and optimal boosting rounds for early stoppage. For this to work, we're going to make this train and predict custom function right here. And the purpose is this script trains an XGBoost regression model for each valid property type. And in this case, it's just single family homes in the Redfin dataset using k-fold cross-validation with a default of 5 folds. It selects the optimal number of boosting rounds using early stopping or stoppage based on the mean absolute error, fits the final model, and outputs predictions along with the feature importance per property type. So we define the XGBoost hyperparameters right here. Regularization, squared error, learning rate 0.1, max depth 3, subsample 0.8, column sample by tree 0.8, and the seed is 42. We make our custom function to train and predict with the log transformed applied. So we have our parameters right here, property type, features. Property type will be single family. The features will be all the columns right here that we get. And our our number folds will be 5. And if there's any empty data, it's just an if else return. But we have property type for all the homes, single family homes in the data set. The X features, so the X is the property features that we're going to use for the model to learn on, and we do a log transform on the target variable. All we have to do is put numpy.log1p and the sold price from our property data frame. And if there was anything that didn't have a price or was empty, it would just fill up as 0. But we have sold prices for all the homes. And then we get a new, so we have a copy, we made a copy of our data frame, and it's property underscore data. And you can see here in the copy, in the features in the X column, and the sold price and the Y. And we're resetting the index right here. And then in this D matrix is kind of it's XGBoost optimized internal data container, kind of like it's like a super data frame, but made just for the XGBoost engine. So instead of storing our features and labels in a regular pandas data frame or NumPy arrays, XGBoost will convert them into a D matrix because it compresses the data to reduce memory usage. It indexes features efficiently for faster lookup. It stores additional metadata alongside the feature matrix, and it stores features, target, and metadata efficiently. So that's why we're using the D matrix. It's an internalized data container for the XGBoost. And in this cross-validation to determine the optimal boosting rounds, we're going to set it as 150 boosting rounds. Number of folds will be 5. The early stoppage is 10. So for each round, we're training on 4/5 of the folds, and we're validating on the remaining 1/5. And we rotate so each fold serves as a validation once. And in this process, we're tracking the mean absolute error for both the train and validation sets. And then for the early stopping rounds of 10, if the validation MAE doesn't improve for 10 rounds, we're stopping early to save time. And then right here, the best number of rounds. The CV results is a pandas data frame with metrics per the boosting rounds. And within that data frame, the IDXM is the finding the boosting round with the lowest validation MAN right here. And then the min gives the value of the minimum MAE still in a log transform space. So boosting round with the lowest validation MAE, and then the minimal value of the minimal mean absolute error. And then the final model training on the full transform data right here. So this is final model equals XGB.train, and then we're getting our XGB parameters, and then our D matrix, number of boosting rounds with the best number of rounds. And then in our predictions in log space, we predict on the final model dot predict D matrix. So D matrix is the data, it was the X, the label is the Y, the sold prices, and the features is the number of features, the columns that we're using the numbers to determine our sold price. So we're doing our dot predict method with the D matrix, and then we're getting back doing a reverse log1p to get our actual sold prices from the predictions log, and we're going to name it Preds original. So predictions original. So that's going to be sold price. Our model prediction sold price. And then we're going to name it, have our data split column, and it's just going to have CV populated in the column for cross validation. And then this is how we get the feature importance. And just to underscore, when we do the final model dot predict right here with the D matrix, we're retraining 100% of the data using the optimal number of boosting rounds found in the cross validation. So just remember, we're retraining on 100% of the data. And then for the feature importance, we're storing our predictions, store our predictions and feature importance right here. And this is going to show as all this calculation. We're returning how much each feature contributes to improving the model, and normalized, so total importance sums up to 100. And then once we get all this, we're going to return our property data frame, address, data split, property type, predicted price, and price. So our model's predictions price, retrain on 100% of the data, and that's coming from this preds underscore original. So we reverse the log1p and in our preds log, and then we're naming it preds original. We're taking it back out of the log1p and putting it back to actual dollar, the actual dollar amount, and that's where we're getting our predicted price and the actual sold price. And you can see here, these are the feature columns that we're using. To run the model, it's an empty list. Then we're doing the for loop to populate all our data. We're using our parameters, so the single family, the property type, and the features are all these features. And here will be included as the model is being calculated. For the sold prices, and the number of folds will equal 5. And once we run this for loop, we create a new data frame, all underscore predictions, which is really just the all underscore predictions underscore list. So this empty list gets populated with the results of our model, and then we export it out here, and you can see here the address, data split, property type, predicted price, and price. And you can see here single family residential, the best mean absolute error based on log scale is a 0.2098 at 80 rounds. And I guess we can think of that as at log scale. So this was before we converted it back to dollar amounts. So the feature importance right here, after we ran this function with the parameters, and baths 38%, 38.7% square feet, 19.1%, waterfront 14.72, private pool 10.68, and so forth. Beds is only 1.56%, lot size only 2.14. And then when we evaluate with the R-square and the MAE, like we've done in the past, start off with this empty Python list, and we're appending this dictionary of data into this empty list. And here's the results that we get. So it's actually 0.978, so that's really good R-square score, and the MAE, mean absolute error difference, is 98,796. So if we see here 0.978, the XGBoost regressor was 0.971, I believe, with the log1p applied. So with our cross-validation best boosting rounds with the log1p applied, we get 0.978. So that's an improvement. Thus, it's an improvement. And that'll be it for this video. In the next video, I'll look at the chart, look at the analysis in our spreadsheet, and just kind of look at the different R-squares and the MAEs for each of the models that we ran. So that'll be it for this video, and thanks for watching, and see y'all in the next video.